Uh, our speaker today is Shintaro Nishikawa, and his title, as you can see there, is Sister algebras associated with real reductive symmetric spaces. Please, Shintaro, go ahead.
Thank you. So thanks for this opportunity to speak. I will tell you some story about C-star algebra, about the real groups and associated with the real reductive symmetric spaces. And this is a joint work in progress with Alexander Afgoustidis, Nigel Higson, Peter Hochs, and Yang Li-san. Okay. So let me start with our favorite C-star algebra, so the reduced group C-star algebra, which is one of our favorite C-star algebra, defined by the regular representation, denoted by lambda g. This is a regular representation acting on L2 space by left translations. And one of the old story about C-star algebra is that G is a type 1 unimodular separable, which is redundant in some cases. The abstract Plancherel theorem, mainly due to Dixmier, which you can find from his book, it says that there's an isomorphism of L2 space of G, which is directly decomposed into B pi tensor B pi star as so this is the isomorphism of the Hilbert spaces. And you can make it the unique with this requirement that f of e is equal to this integration of the trace. And this is the abstract theorem by Dixmier, the Plancherel theorem. And this isomorphism on the left is an isomorphism of the unitary representation of G times G. So on the left, you have G acting on the left and the right representation, right regular representation. And on this part, G is acting on B pi and B pi star. And just in case, I will remind you, so B pi is a unitary representation of G, then pi star, I define it as a dual, or sometimes called contragradient, and it's defined on this space of linear functional, B pi star, and defined by this formula, pi star of G, it's pi G inverse star. And the one remark is that this space B pi star, sometimes identified as the Hilbert-Schmidt operators on B pi, because of this isomorphism, B pi tensor B pi star, the isomorphic to B pi tensor B pi star. Yeah, so this is one of the quite often cited theorem of Dixmier. And then the support of mu is what we call the reduced dual of GR. So mu is a measure on this G hat, which is the nice measurable, nice space in the case of G's type 1. And then this measure mu has a support, and that's coincide with the spectrum of C stars of G, the space of the irreducible representation of C stars, reduced C stars of G. And I want to discuss what happens if you consider a G as a symmetric space, X equals G times G, modulo diagonal subgroup of G, which is a perspective which is quite common in harmonic analysis. And then, of course, it's just same as saying you consider the representation of G from the left and then right, G acting on the right at the same time. And this has been studied in other perspective, for example, in a discrete group setting. But I will give you some new insight that at least from our perspective, this was quite new that when we discovered this perspective. So let me give you some story about this, especially in case of this type 1 setting. Okay, so do you understand what I want to do? I just want to consider this image quotient of C star G times G acting on L2 space of G. I think you can imagine many things right now because I didn't specify anything. Our assumption is G is type 1 in unimodular, so most of the discrete group you are interested in is excluded. Okay, so let X be a G times G mod diagonal G of G just for the notation. and I let A be this quotient of G times G. So that's the quotient of the C-star algebra of G times G. Then what we can say from the abstract Plancherel theorem is the following. So the spectrum A hat is canonically identified as just the pi tensor pi star, where pi is the unitary dual, and then take a closure because it has to be closed subspace. And this follows just by abstract Plancherel theorem, which is applicable even for just the tracial representation of type 1 C-star algebras. So this is some closed sets in GR hat times GR hat. Yeah, so as I said, A contains pi tensor pi star, but also the limits of those points. And we can wonder already what the C-star algebra A looks like. And then sometimes it's kind of ugly. Sometimes it's okay. But it's just a C-star algebra you can define canonically, right? And then you can also think A as just a quotient of reduced groups of C-star G, minimal tensor product with C-star G, with a spectrum pi tensor pi star closure. Okay. I want to remark one thing. So I want to study the set pi tensor pi star, but you can also think pi tensor pi, and sometimes this is more canonical because it's diagonal. So there's identification. So if you have a map, for the group which sends F to F conjugate. So it sends value of F at the G by conjugate of F of G. And this map induces automorphism on C star G, which is antilinear, but it maps the primitive ideals I pi to I pi star. So this gives you a homeomorphism from on the spectrum, which sends pi tensor pi star to pi tensor pi. So as far as the topology is concerned, you can study pi tensor pi star and pi tensor pi in a parallel way. Okay. So anyway, so this pi tensor pi star, this is the elementary point. Pi tensor pi star is closed in GR hat, if and only if pi tensor pi is closed. That just means GR is Hausdorff. So unless GR is Hausdorff, this contains many limit points. So far, so good. So this is fact. Of course, sometimes this GR hat is a Hausdorff, in which case this closure coincides with this skew diagonal. So that's also an interesting case that I also included in the example. Okay, so what I want to talk about this. So I think it's nice to consider first a baby example. So let's consider any type 1 C-star algebra and then consider quotient A of B tensor B. Okay, so forget about skew diagonal pi tensor pi star, but let's consider some general situation. So take a C-star algebra, take a B tensor B, and then take a quotient pi tensor pi with a spectrum pi tensor pi closure. This you can always do for type 1 C-star algebra. Yeah, it's a funky things to do, but you can do this. And then, well, let's see what happens. So take a B equals C0 R equals C2. So this is a flip action. So it's you can identify this as, if you like, a subalgebra of this cone of M2, where at the origin it's a diagonal. So you frequently encounter this spectrum, this non-Hausdorff spectrum, the half line with the double points at the origin. So this is a non-Hausdorff example of a spectrum, the one of the easiest one. This example shows up in many places. Then consider B tensor B, right? And then take a quotient corresponding to pi tensor pi. And then if you think a little bit, what you get is the C-star algebra, which is just the cone of M4, but now at the origin, you have 4 points, right? So this is, if you think a little bit, occasionally are different from these C-star algebra, but there's an ideal I of A whose spectrum is pi tensor pi. So if you keep track of which points are pi and then pi tensor pi and pi 1 tensor pi 2 and so on, you extract only 2 points of these 4 points at the non-Hausdorff points. And there's an ideal corresponding to pi tensor pi. And in fact, you can also show I is Morita equivalent to B. So this is a baby example, but what I'm going to tell you is that this situation, so you take a B tensor B, take a quotient, and then you look at the this ideal then you find some Moriteq web. This happens for any linear connected real reductive group. So this is one of the first thing I want to tell you. It gives you idea that, oh, so real reductive V group that people love, it's quite special because as I will also say, it's not common that this kind of Moriteq covariance is obtained. Okay, so this is a theorem. I want to first give you. So following that, I will say, so there are several definitions of real reductive group, but here is the simple one. G is a linear connected real reductive group if it's closed, a connected subgroup of Gn and R, stable under transpose. So that includes SR and R, SO and M0, or any complex semi-simple E group with finite center, and so on. Okay, so the first theorem says that if G is a linear connected real reductive group, then consider this diagonal. And then, as I said, you can take this quotient A, which is just the same as considering the quotient of the regular and the right regular representation of G times G. Then the statement is that there's an ideal I of A whose spectrum is pi tensor pi star. So that's just same as saying, in other words, the skew diagonal is open in its closure in the spectrum. So the ideal is unique if you specify like this. And then moreover, this ideal is a Morita equivalent to reduced group C star algebra. Hence, they have an isomorphic K-theory. And it's kind of exciting because, C star algebra G is one of the most studied C star algebra, and their K-theory is very interesting. And then we have other canonically defined ideal inside the quotient of some bigger algebras, which have isomorphic K-theory. So a lot to think about, but it's quite mysterious from our perspective yet. So, but anyway, this is a theorem. And the same assumption in G, you have also the diagonal because of the thing I told you. You have a homeomorphism. There's a similar story if you consider diagonal. And then again, the corresponding ideal quotient is the Morita equivalent of C star. So that's the first thing I wanted to tell you. But what I want to tell you is that this property is quite uncommon. You can think if you're relaxed, you can think just 10 minutes or so and then find many counterexamples for the similar statement for any type 1 C star algebra. But I will give you anyway in this next 2 slides. This is uncommon for other groups G and for type 1 C star algebra. So as I said, this exemplifies that real reductive group, connected linear reductive group, it's so special, right? It has very special feature that.
May I ask a small question? So in these cases, what is the quotient by the ideal?
Quotient by the ideal, it gives you C star algebra. If you like, the C star algebra of G times G, a quotient of C star algebra G times G supported on the boundary, right? So the pi tensor, you have a pi tensor pi star, and then take a closure. Then there's a boundary, which is the limit point of pi tensor pi star, which is not the pi tensor pi star. So it's some.
Yeah, but so what I meant, what I had in mind is, you identify an ideal of an algebra with up to Morita equivalence with some known algebra, right?
Right.
Okay, which is the reduced system algebra. And then,
right.
Well, I was thinking for the purposes of calculation, whether this put the C-star algebra of G in a sequence in which you might know the other 2 terms, something.
Yeah, to be fair, I'm not 100% sure what you want to achieve. So for example, if pi tensor pi star is Hausdorff, then ideal I is the A itself. So the quotient is 0 in that case.
Okay, so A is just C star of G up to Morita equivalence.
Up to Morita equivalence.
Yeah. Yeah, but that cannot happen in the case of the second theorem, right? Because C star of G times G will not be
right.
the single code.
Right.
So it's not the equivalent, it's not okay. Okay.
Yeah, if you come up with more questions, let me know. Maybe we will find some more to discuss in due course. But thanks for that. Okay, so but what I want to tell you is that, okay, let's go back to the simple type 1 C stars row or more general C stars row setting. I will tell you this is very uncommon. And I think you will be convinced with this next 2 slides, or maybe 1 slide. Okay, but let me start with this simple topological fact. So since which I didn't know before. So X is a topological space and the diagonal, consider diagonal. And consider the property that the diagonal is open its closure. It's the same as saying it's a locally closed. Then this is if and only if X is a locally Hausdorff. I mean, you might think, oh, this is tautological because delta X is closed if and only if X is Hausdorff. So of course, it's a locally closed if and only if locally Hausdorff. If you're satisfied with that, that's fine. But in case you wonder, this is just a proof. Yeah. So it's just some fact. But this is the relevant property of the spectrum that we are studying. This is a diagonal, and then we are taking a closure. And we are studying if it's open in its closure, because that corresponds to the ideal in the quotient. So this is the relevant in our story, and this is exactly the characterization. We can find some ideal I if and only if your spectrum is locally Hausdorff. So let me give you an example. So the half line with the 2 points at the origin, the example I told you, this is locally Hausdorff because, I mean, it's there's only one non-Hausdorff point. You can remove 1 point by open set and so on. This is a T1 space. But as soon as if you have a non-closed point, if you think about it, if you have a non-closed point, then there's no shot that the A hat is locally Hausdorff, because if it's locally Hausdorff, then the point has to be closed. So most of the thing at type 1 C stars, right, you cannot find the ideal which has spectrum pi tensor pi, for example, 2-Pritz algebra, or you name it. Okay, so this is you need all point to be closed. So that's restrict our attention to very small class of type 1 C stars, right? And moreover, okay, so what about the other examples? What about the Heisenberg group? This is a nilpotent group, simply connected nilpotent group. And each point is closed in a spectrum. So this is the Heisenberg group. A, B, C are reals. Then the unitary dual is not locally Hausdorff, unfortunately, because G hat is roughly looks like a real line, but the point is replaced by a plane at the origin. And if you think about it, you cannot separate these non-Hausdorff, any 2 points in this non-Hausdorff plane. No, sorry, you can separate by open set, but I mean, if you try to find a locally Hausdorff open subset, then you can't, because if you take non-Hausdorff plane, take an open set, then it contains a real line, a portion of the real line, which converges to the entire plane. So that's prohibited. So this is not locally closed. Again, for this example, if you try to come up this ideal I, which has a spectrum pi tensor pi, that fails. So that's unfortunate. So most of the C stars where you can think of, they don't have pi tensor pi spectrum. Okay. So far, so good. But okay, so what if it's a Hausdorff, right? This is the best situation. But then you can, of course, consider this quotient A of B tensor V with the spectrum pi tensor pi. This is just a quotient of B tensor V. But they're not often Morita equivalent. And most of the time, they are not Morita equivalent. I'll give you 2 prominent examples. So let's first example is this. I think this is kind of analog or cousin of the dimension drop C stars burst. So take a cone of M2, but at the origin, you take a scalar matrix, right? Then you can just compute the short exact sequence. K0 is 0 and K1 is 2. But if you take the diagonal, then that's going to correspond to take a tensor product and then take a diagonal. So that corresponds to just the cone of M4, but the origin is a scalar. So K1 is 4. So they have the different K series. So they're not Morita equivalent. And more topological example that some of you might like is take a B continuous trace C star algebras. So it has, of course, Hausdorff spectrum. Then according to this very beautiful Dix-Meade-Doherty theory, you can take this A, which is the tensor product of B over X. So continuous trace C star algebra corresponds to the bundle of compact operators over the space. And then you're taking an interior tensor product. Then it's Morita equivalent to B if and only if their invariance is coincides. So if delta B plus delta B equals delta B in the sum cohomology theory, and that's same as delta B equals 0. And same if you replace this B to B opposite, which is more about the skew diagonal, then it says delta B minus delta B equals delta B. So that's also delta B equals 0. So that happens only if delta B equals 0. That's when this guy B is already some it's a compact operators on some Hilbert space bundle over X, right? And then in this case, it's easy to see A is Morita equivalent to B. So if you take a tensor product over X, so this guy is Morita equivalent to B by just, you can also, I mean, it follows from this theorem, but also you can directly look up this continuous field, Morita equivalence. So it tells you that whatever the reduced group C stars are linear reductive connected real reductive Lie group C stars were, this is more close to this situation. And this situation is kind of the closest description of the C stars group G. It's a kind of trivial bundle, and then you take a compact operators. So that's why it's a theorem holds. Conversely, if you have such a this multiplicity 2 situation, then you would never hope that the theorem to be true because this, I mean, Morita equivalence restrict to the any closed subspace of the spectrum. So if you have a multiplicity jump phenomenon like this, you wouldn't get this Morita equivalence. So these 2 examples kind of tell you a lot about restriction for this pi tensor pi to be Morita equivalent to pi. Sorry, the original one. Okay, so that's, I hope I may convince you that this is quite an uncommon property. Okay, but it's true for real reductive groups. And I'll tell you, well, sorry, this is I will come back to this later. I think I had the wrong order. So I want to tell you some main ingredients of the proof. So it's a 2-step, and one is more, I think many people know. So for G real reductive in Harish-Chandra's class, so this is a slightly bigger class of real reductive group I was talking about. This contains a disconnected class, also a coupling of some SL2R, which is nonlinear and so on. So this is a class that Harish-Chandra studied, and then one of the major results of his is a Plancherel decomposition of this short space. I will not go into detail, but this is a subspace of L2G. So if you manage to decompose this nicely, then you will also get the Plancherel decomposition of L2 space of G. And also, it's also at the same time, it's a dense subalgebra reduced group C star G. So again, if you have a nice decomposition of C of G, you can translate it into a nice decomposition of reduced group of G. And that's what Harish-Chandra did. And the corresponding decomposition, although you can make it be nice and friendly to C star algebras and then using Hilbert module, and then that was done by Claire, Crisp, and Higson. And this is the like a 2-line summary. So first, this reduced group C star algebra for this class is the direct sum of some finitely direct sum of some C star GP. This is a direct summand. And P is some equivalence class of parabolic subgroup, which I don't go in detail, but this is also, this set is bijective to equivalence conjugacy class of Cartan subspace of G. Okay, so the C star G of P is now isomorphic to this nice direct sum. This is C0 function on A, or compact. So it's very simple C star algebra. It's just a C0 of A valid in compact. A is a vector space. And then there's a WP, which is some root reflections acting on both this algebra and this parameters. And then this parameter is some discrete set of parameters called the discrete series representation of some group. But we can ignore most of the thing if you are not familiar with this. But so the upshot is that this guy is direct sum of much simpler one, C0 of A compact of W invariant, where W peak psi is again root reflection acting on this space A, but also on the compact operators. So unfortunately, for the sake of time, I will omit more explanation. But again, the point is this spectrum, the GR, which we are interested in, is just a direct disjoint union of these simple guys. So whatever the spectrum property we want to study, it's reduced to the study of this guy. So this guy, yeah, we are interested in whether this spectrum is locally Hausdorff or not, because that's the theorem in replaced way. So it's the question reduced to this question. You have CZ of A compact, and then that some finite group is acting on it. Is this a locally Hausdorff or not? So the answer is, if the action is arbitrary, that's not true. I will give you a counterexample due to Bogan. But in a connected linear real reductive, these four adjectives, then there's a theorem which says this guy is much simpler, and then that's why it's a theorem holds. I will tell you this extra ingredient. So now I want to assume this connected assumption, which is crucial. So G is connected and linear. Then there's an extra feature of this each summon, C0 of A compact of W fixed point of C0 of A compact. And this is due to Knapp and Stein, but also separately by Bogan. Okay, so I mean, of course, their theorem is pure representation theoretic, but I will just extract only the relevant information in terms of C-star algebras. But I want to first let K to be maximal compact subgroup of G. So this is some compact group. And for each peak psi, so forget about P and psi, it's just I fix the parameters. So I will consider this summoned. Then there's a canonically defined finite subset of the irreducible representation of K. So it could be 1 or 2 or 4. The finitely many irreducible representation K hat with the following properties. So take Lancome projection P tau in C-star algebra of K. So that's in the multiplier algebra, reduced group C-star algebra. In particular, it acts as multiplier on here. So you can multiply by this P tau on these algebras. So this is a Lancome projection corresponding to this representation tau. And then, so this is not it's a central projection. I took a Lancome projection inside the compact operators on this representation tau. Okay. And then you can multiply, and then you can take a corner of this. And then the theorem, or the corollary of their theorem, is that this is going to be abelian. So in other words, this is a minimal projection or abelian projections inside this guy. Or that's not quite precise because P tau is in the multiplier algebra. But it says that its multiplicity is 1 in the representation that occurring in this series. These are types. Okay, so this corner has a spectrum, Hausdorff spectrum. And then moreover, if you take the corresponding ideal, and then if you take a finite sum over this finite subset, you get the entire things. And what this says is that this has locally Hausdorff spectrum because you have a finitely many ideal. Finite is not necessary. You have an ideal, and then each ideal gives you open set, and then each ideal has Hausdorff spectrum. So this is why it has a locally Hausdorff spectrum. So ultimately, it comes down to this multiplicity 1. So this theorem I'm implicitly citing is called the multiplicity 1 theorem of Knapp-Stein. Right, so this is the extra feature of this summon, which is only available, well, not only, but which is available for connected and linear assumption. I will give you some example that I skipped, that this is not true if you just slightly away from connected. So this is very special feature, but unfortunately it's not generalized, it's too much. Okay, so sorry for going back. So there's a linear disconnected real reductive group G such that this GR hat is not locally Hausdorff. Okay, so this example is essentially due to Bogan. So G equals SO2R, and it's very simple example. And what this is, you take just SO2R and SO2R, and then you consider 8-element quaternionic group. So you have I, J, K, and then I, J is K, and so on. And then this guy has a center, but center acts trivially, and then I acts by automorphism factor through O2, and then J acts by automorphism factoring through O2 on here. So it's just the inner action inside GO2. So this action is quite simple-minded. Okay, so I mean, the point is the center acts trivially. Okay, that's the only thing you might want to remember. So then just the C star G contains a direct summon. So for this G, so this, you see this is disconnected. C star G contains a direct summon, and then long story short, that is Morita equivalent to the following C stars. It's very simple. So it's a cone of M2C, tensor cone of the 0 infinity cross 0 infinity, and it's a diagonal matrices at the wall, 0 R and R0, but also it's a scalar at the origin. So this is, sorry for poorly drawing pictures, but this is the picture, right? So this is M2C here. This is scalar. This is C plus C, that's the diagonal. This is C plus C, the diagonal. And also you can read off the spectrum from this. You see, this is just a unitary dual of this guy. It's such a simple-minded C star algebra, but this is not locally Hausdorff at the origin. So as far as I know, I mean, this is one of the simplest non-locally Hausdorff C star algebra, which you can cook up using just the intervals and M2. So why this is not locally Hausdorff? Because I mean, this is take any open neighborhood here, then you see there's always no Hausdorff point. If this C is not a scalar but multiplicity 1, for example, then it's you can separate. You have open set which contains only the let one, for example. Then that's going to be Hausdorff. So this has multiplicity 2 is the problem. If this has multiplicity 1, we can use the technique which I kind of described. You have a projection, and then there's a corners. You're breaking into pieces. Each piece is an open set, which is the commutative. So anyway, this is kind of funny, interesting example. You can replace this if you like discrete group, you can replace this SL2R to Z, integer times integer, and then do some quaternion group acting by automorphism syntax trivially. You get the similar picture, but replaced by torus. That's another example. Is that all right? So long story short, for where was the theorem? So for linear connected real reductive groups, you have this ideal, which is pi tensor pi star or pi tensor pi, whichever you like. And then that is this canonically defined ideal, and then that's equivalent to saying the spectrum is locally closed. And moreover, that's Morita equivalent to reduced group C star. But that's very special for linear connected reductive group. If you go beyond a little bit, far from connected, then it's no longer true. And as we saw, this is not even close if it's not reductive. Okay, so but that's the story I wanted to first tell you. Is there any questions?
So far, so good.
Excuse me?
No, I was saying this. Go ahead.
Oh, okay, thanks. Okay, so that's a story about the G. If you look at the G as G times G mod G. Okay, But the reason I mentioned this is that that's a special class of so-called real reductive symmetric space. So, of course, you can study more general homogeneous space, but there's a special class called the real reductive symmetric space, whose harmonic analysis is well studied and very beautifully described in a very advanced representation theory. And then so homogeneous space is called real reductive. If G is real reductive in a sense I described, for example, and then H is a symmetric subgroup of G. So that means H is an open subgroup of G sigma, where sigma is an involution. There are many examples. And then the example I gave you, G times G mod diagonal G, is an example of this kind, which is called group case. But there are many other examples, like SLN C mod SLN R, or this GLM M plus N mod GLM plus GLN, although this is not connected, it's fine. But this space itself is connected, I think. And here its involution is inner, right? It's just 1 minus 1. So many interesting involution is just the inner one. It's just the adjoint by some self-adjoint unity. That gives you an interesting example of symmetric space. And although these two are not the inner action. Okay, so there are many examples of a symmetric space. And from what we just saw about the group case, which is G times G mod G, you can kind of convince that, okay, you can first study regular representation, but that quotient, fine, that quotient is some C star as well, but that may contain some proper idea that deserves some attention, at least in terms of K-theory. And that was kind of motivation we had in the beginning. And it turns out this is far more complicated than we thought. But I will tell you some aspects that are nice. So I just recall, for example, in the group case, it has an ideal Morita equivalent to reduce group C stars per G. But that's not the entirely the quotient, but the proper ideal unless G1 is a Household spectrum. And also, we also know that this is quite delicate question because this ideal that doesn't exist. Like there's no ideal which has pi tensor pi star as the spectrum, unless this one is a locally Household. So that was a kind of delicate question. But we wonder, what can we say about the symmetric space case? And then there's a situation, there's an analogous story you can tell. So there's a spectrum that this is not a pi tensor pi star, but you can define some subset of the unitary dual that's kind of captures what you want. Like in the case of group case, you want this subset. Similarly, you want for symmetric space G mod H, you can define some canonically defined subset. And then the question is that locally closed. Then you want to define that ideal, and then you can study K-theory. And the situation is much more complicated. Unfortunately, I will not go into detail on that direction. I will focus on some aspects that are easy to digest, which is the case when basically it corresponds to the case when G1 was the Household spectrum. It's similar to that situation. But I will first give you what was known by skipping some details. So this is one of the things I wanted to let you know if you didn't know. So this Harish-Chandra Plancherel decomposition, which I told you, which everybody likes, this amazingly, this has been extended by Van den Van, Delorme, and Schlichtkrull in 90s, called Plancherel theorem for the Schwartz space and the symmetric space G mod H. Their work was based on, building on the work of other people, the French Tettienzen, Oshima Matsuki, and other people on the discrete series representation. So that's a separate story. You want to first study irreducible direct sum of L2 space, and this is very hard, but there's also a beautiful story to tell. The building on this work, they obtained this Plancherel decomposition, which is completely analogous to the Harish-Chandra decomposition. So again, I'm sorry for skipping detail, but there's a Schwartz space, C of GH, that's a smooth subspace of L2 space. And that, again, decomposes into direct sum, finitely direct sum of nice pieces. And then each piece looks like what we saw in the group case. It's some Schwartz space of functions, values in the vector space, and then you take a fixed point by some root reflections. You see some many technical notation here, but you can ignore it. I just want to tell you that you see, it's a miracle that you have analogous story like this. You have a nice decomposition, and this is just the function on the AQ valued in big Hilbert space, and on generic fiber, this corresponds to irreducible representations. So this parameterizes representation happening in L2G mod H into irreducibles nicely into specific forms. So to be precise, I should have considered some dense subspace of that, and also abuse some notation. But the message, I hope the message was that there's a beautiful story here. But the crucial difference I want to tell you is that the group case, C of G mod H, which was a C of G times G mod G, was a C of G, and that was the group, basically the group algebras, a dense subalgebra, group algebra, which many people in non-commuted geometry have used at some point. But this is not an algebra at all. This is just a C of G mod H. As you see, it's just a Hilbert space H, and you can ignore this B, but it's basically a Hilbert space H, not the Hilbert-Schmidt space. It's just the H, not the compact of H. It's just a vector space valued in H, not an algebras. And the long story short, it is not straightforward to transfer this decomposition into this decomposition of the quotient. So you take a quotient of C stars, the maximal group C star of G, and then take a regular representation. You can, of course, take a quotient. And then first thing you can ask is, what's the decomposition? Do we have analogous decomposition like a reduced group C stars, bro? Yes, we have a kind of decomposition if you try to use it, but it's not straightforward. And it also, it doesn't translate well in general. Again, because this is also not because this is not an algebra. But I will tell you, in some cases, the Plancherel theorem is more than enough to fully determine. We are too ambitious. We are talking about the more general reductive symmetric space, which contains the group case, G mod G, as a very special case. And we went beyond the too much general classes. And I will tell you, some modest class of symmetric spaces, you have a very nice story. Namely, you have a complete understanding of the group C stars from K theory. So that's I want to tell you in the last 10 minutes or so. But I thought, I think it's good to tell you about some class of symmetric space that is called the tempered symmetric spaces. And so symmetric space, or more generally homogeneous space G mod H, you can study this question. Consider the regular representation on L2G mod H, and you consider the support of this regular representation. In other words, the spectrum of the quotient of the C stars burst. And you say it's tempered if it's just contained in this reduced spectrum. So that's just same as saying regular representation factors through reduced group C stars burst. And here's an amazing result or work of this Bruno and Kobayashi. They classify all reductive pairs GH such that this G mod H is not tempered, or in other words, it's tempered also, vice versa. And in their work, also they show that, in a part of the work, they show that if you consider the complexification, this C mod HC, if this is tempered, then G mod H is tempered. So this condition is a stronger assumption of the temperedness. And I want to describe this condition because it's very simple and it's very useful. Okay. So for symmetric space, the condition of GC mod HC is be tempered is the following. Again, so GC mod HC means you complexify everything, the G mod H as a real, you consider G mod H as a real analytic space and then complexify it. You get the complex homogeneous space. That's what a notation suggests. And this being tempered is equivalent to the following. If you take a Cartan subspace of B of Q, here Q is the orthogonal complement of the real algebra H in G. So you take a Cartan subspace, the maximal abelian subspace, which consists of semi-simple elements. You take a centralizer, because it's not the entire space, not the H, not the G, but only on the complement. the centralizer may not be abelian, but if it's abelian, you call it well-tempered. And that's precisely the condition for GC mod HC being tempered in the case of symmetric. So this is very simple criteria that you can explicitly check in many cases. And as I said, any well-tempered symmetric space is tempered, and then if G mod H is complex, then the converse holds. And you can also deduce this fact from Plancherel theorem, which is, of course, overkill, but right. So I mean, why we are happy? So if for G mod H for this class, you take a quotient of the maximal group C star algebra, that's going to be a quotient of the reduced, and the reduced group C star algebra is well understood. So this class is easy to study, right? So it's the first place to look for about symmetric spaces. And I just wrote the examples of well-tempered homogeneous space. So it contains group case. You can check. Also, this SLM plus N mod SOMN, SUMN mod SOMN, and so on and so forth. And what I want to tell you is that this condition is very easy to check. You take a complement of the H, and then take any maximal abelian subspace, and then take a centralizer if it's abelian, if it's tempered. If not, it's not. So that's a very nice thing. And again, that's good to tell you if it's a reduced group C star algebra, the regular representation factors will reduce or not. So it's very nice work, very fantastic work of Bruno and Kobayashi. I just wanted to advertise this. Okay, so that's the first restriction I want to pay attention. I want to impulse for today because situation in general is more complicated. But I will tell you, I will further restrict our attention to when G is complex. And then among them, there's a nice class which is called a GC mod GR. So that's the symmetric space I want to talk about today in the rest of the talk. So let's G be connected complex to the reductive B group and take any open subgroup of its real points. So for example, SNC mod SNR, or if you take any real group, you have a canonical way to, well, not canonical way, but if you have realized that the real matrices, you can always complexify. That's going to be complex Lie group, and then you can take a quotient. There's a Riemannian example. You take a maximal compact, there's a canonically associated complex and simple Lie group, and take a quotient. That's a Riemannian symmetric space, but it's a case. This is also GC mod GR. Okay, so this is, I mean, for the first time, you might think this it's kind of surprising. This is a well-tempered, but these guys are well-tempered, namely the regular representation factors through reduced group C star algebra. It's kind of surprising, for me at least, that the disk, for example, if you take a regular representation, it factors through reduced group C star algebra. I mean, if you're so used to amenable actions and so on, then you might expect, oh, your group, your quotient must be amenable or something, but that's not true. This quotient factors through reduced. So this is a class called, I call it type GC mod GR, and then Plancherel formula was obtained by Pascal Link, and before this more general theorem I told you. Okay, so this is a class I want to pay attention because we can describe the K-theory and C star algebra for this class very nicely. So that's the next almost last slide. So here's the theorem. So if you have a G mod H, a symmetric space of type GC mod GR, so any of the form complex mod real, then actually it can happen that K-theory is 0. Not the Riemannian case, but there are many, many cases where K-theory is 0. And then K-theory is non-zero if and only if the following equivalent condition holds. So the first condition says that if you have a Cartan subspace AH, a P cap H, so this is a Lie algebra of H. This is a self-adjoint part. So this is the part of the Cartan subspace of H. If you take this guy and then you take a centralizer in H, that must be abelian. And if you know a term, this is called then people say H is a quasi-split. So vector part, this is a vector part. If the vector part, sorry, the maximal split Cartan, sorry, I think I mixed up the explanation. But anyway, so maximal abelian of P cap H, you take a centralizer, that's abelian equal to H quasi-split. That's if and only if K-series is non-zero. And that's also, if you take a multiplication by I, it just corresponds to this condition. if you take a Cartan subspace TQ of K cap Q, so Q is the orthogonal complement of H in G. So K cap Q is, again, this is not the Cartan subspace of compact. It's a subpart of the Cartan. And you take a centralizer, that's a baryon. But the fourth condition, it's kind of easy to understand. So that's equivalent to the following. So it's same as saying G mod H is GC mod GR, but there's a compact part, which is K is a maximum compact of G. You take a K cap H, that's a compact symmetric space. You get this compact symmetric space. And this is, of course, tempered, but I'm saying this is well tempered. That's what I mean is its complexification is tempered. If that happens, then K series is non-zero. If that doesn't happen, K series is 0. So there is a dichotomy between the two.
Sorry, a stupid observation. There must be a congruence there instead of an equality, right? Congruence mod 2.
Congruence. Congruence.
Mod 2. In the star, so the star is mod 2, right?
Right. Yes. It's mod 2. Right. Thank you. You're looking here, right? Yes. Sorry. Yes. This is mod 2. Z mod 2. Thanks for the remark. That's very important. Yeah, it's a periodic, periodic cohomology. What do I want to say? So in the case it's non-zero, you have this description. It's 0. So this really behaves like when reduced group C star algebra of the complex reductive group. The case theory behaves like that. It's a 0 and on one dimension, and then on the other dimension, it's a direct sum of Z parameterized roughly by representation of K. But this subscript K cap H means representation of K with the K cap H fixed vectors. So there's a special class of representation of K, which occurs in K mod K cap H, this space. It's called, and I call K cap H, sorry, K sub K cap H. And then regular means a regular part of this representation, which...
Sorry, is the number of summands in that direct sum usually finite, infinite, or what?
It's infinite, almost all the time, except some degenerate case, for example.
So you cannot distinguish two of them by the K theory because,
no,
and it's infinite. Yeah. Okay.
Yeah, but that's true for any complex reductive group. I mean, K theory is most of the time just like sum of infinitely Z. Right. What is interesting is that this is so G is a complex GC, and then if you ignore this K cap H, then that corresponds to roughly the K theory of the ambient one, reduced group C star GC, and you can take a quotient map, the reduced group C star of G to this guy, and that's going to be almost always 0 because of the dimension shift. And then but this is clearly related to Dirac induction somehow, but there's a bottom up missing, and so this dimension shift, and we don't know how to make an interesting, say, KK element or so to connect this story to Baum-Cohn conjecture. That's we don't know, but it's kind of exciting that you have a K theory which is parameterized nicely like this. But this is as I said, it's a best case scenario, and I also emphasize that this can be 0 unless this is condition is satisfied. Okay, but thanks for asking, and then I should finish very soon, right? So this is the last slide. So I would this is kind of remark related to the last one. So if you have a symmetric pair, if G mod H, so it's defined by involution, H is a subgroup, open subgroup of G sigma, then you can always define some companion, GH prime. And H prime is defined by the other involution, theta sigma. And here I have to assume the involution commutes with the theta, which is Cartan involution. And the Cartan involution is the one whose fixed point is a maximal compact. And you can arrange so that sigma and theta commute. So this is well defined if you arrange like that. Okay, so there's a companion, and then there's duality. And if you do it twice, then you go back. So there's kind of a nice duality between the two. If GH is of type GC mod GR, if you do this, you get this companion KC K cap HC, which appeared in this condition, this condition KC mod K cap HC tempered. So this companion is this complex homogeneous space defined by the whose real part is K compact symmetric space K mod K cap H. And yeah, so the condition of the previous theorem that the K series is non-zero was precisely that this pair is tempered. So the symmetric space is tempered. In this case, so suppose K series is non-zero for this guy, then you have a similar decomposition. So it's basically the same, except the dimension is different. It's kind of a complement each other. You have a complex unitary dual, which is a plane, and then you have one direction and the other direction in transversal, and then this is what happens. You have one dimension TH, dimension TQ. If you add them up, it's going to be a cut-down subspace of K. So yeah, it's again, there's something must be told about this story, but we haven't have a complete picture in terms of MCG. But it's kind of nice. We have a duality between these two. But I should emphasize this duality does not hold without this tempered assumption. And there's the simple-minded example. Take G mod H to be KCK. So this is the Riemannian case. Riemannian case, you always get the K series 0. That's just a simple fact, maybe, which I should have mentioned. If you consider Riemannian symmetric space, you get K series 0. Then in this case, sigma is zeta. So if you compose sigma and zeta, you get the trivial involution. So the fixed point is Kc. Then if you take a quotient, of course, you get the trivial, trivial C stars versus just the C, trivial representation. It's not tempered unless it's abelian. So in the case of abelian, this fits into this framework. If not, they have a different K series, Z for this KC, and 0 for this Riemannian case. If K is abelian, it fits into this framework. If K is abelian, there's a trivial representation, which is Z, of course. But if it's abelian, KC mod K, it's just a line. So again, it's K series Z for the dimension of the plane. So that fits into this picture. So sorry for rush, but I wanted to tell you there's some beautiful theory to tell, but the situation, I should emphasize, situation is much more complicated for more general reductive symmetric spaces. Yeah, thank you.
Thanks for your nice talk. Are there any questions from the audience? Well, I already did my job as a host and asked several stupid questions.
So, no. Thanks for your question.
If there are any, yeah, okay. So if there are any questions, I will stop the recording now.